Good morning, students. Today we will discuss dielectrics. What are dielectrics and what are the different types of dielectrics? So here you can see that dielectrics, these are nothing but insulating materials and which can transmit electric effect without actually conducting electricity. See, these insulating materials cannot conduct electricity, reason being their electrons are very tightly bound. So they cannot make us available free electron. Free electrons are not available for conduction, but still they can transmit the electric effect without conducting. How? We will understand. Here these dielectrics are categorized as non-polar dielectrics and polar dielectrics. So non-polar dielectrics, these are the molecules in which center of mass of positive charge coincide with the center of mass of negative charge. Like whatever molecule we have taken, their positive and negative charge will coincide. Then that molecule will be taken as non-polar molecule. Means, how can we understand it? Like this is a molecule where positive and negative charge are coinciding. These are not separated from each other for non-polar molecules. So in this case, there will be no net dipole moment because the molecules positive and negative charge are not, these are not separated. So correspondingly, it will not have any dipole moment. So this is having zero dipole moment. The molecule has zero dipole moment. So example can be hydrogen, oxygen, carbon dioxide, methane, and many more examples can be. In detail, you discuss all these concepts in chemistry. Now, non-polar molecules have symmetrical shape. What about polar dielectrics? Polar dielectrics are the dielectrics in which molecules are arranged such that in which center of mass of positive charge and negative charge, they do not coincide with each other. How? As we can see, this is here center of mass of negative charge and positive charge are not coinciding. These are separated. Whereas in non-polar molecules, these are coinciding with each other. This is the basic difference. So in this case, you can say these molecules have unsymmetrical shape and they have certain permanent dipole moment. Like what can be the examples you can take here? Now, so here these molecules have unsymmetrical shape and they have some permanent dipole moment. Why they have permanent dipole moment? Because the charges are separated. So when they are separated by certain distance, so they will have some dipole moment. Now example of these can be water, hydrochloric acid, ammonia, carbon monoxide, etc. Now when we have studied the basic difference between polar and non-polar molecules, so basically what happened, how this dielectric material transmits the electric effect without conducting. So here we will study the concept of polarization, which is nothing new, that is the concept related with charging by induction method. So here see, when we are discussing with the dielectric polarization, so when non-polar molecule is placed in external electric field, what will happen in that case? See here, when we are taking non-polar molecule, we are taking, these are the plates which are enabling some electric field to be applied. And when some non-polar molecule, initially this non-polar molecule is centered and positive and negative charge are coinciding. But as it is placed in external electric field, then what will happen? Its negative and positive charge will be slightly separated. So correspondingly, due to the stretch of electric field, it will have certain dipole moment. So when some non-polar molecule is placed in this external field, the center of positive charge, it is pulled in the direction of field. See, here it is pulled in the direction of field, and center of negative charge is pulled opposite to direction of field. So now you can say the molecule will get polarized. Polarized means then it will have certain dipole moment. Now, so this was the concept of non-polar molecule. Now if we take polar molecule, Initially, as we know that the polar molecule have some dipole moment, but when there is no external field, if it is placed in a region when there is no impact of electric field, then what will happen? These dipoles are oriented in such a manner that the net dipole moment will be 0. That means their random motion will be there. Randomly they are oriented. So you will say there is a random orientation in such a manner that the combined effect, the net dipole moment of the complete dielectric will be 0. Why? Because these molecules are arranged in a different manner, in different direction. So what is the purpose of external electric field? When you can say that this polar molecule is placed between some external field, then, or you can say any dielectric is placed between, so then what will happen? All the dipoles are aligned in these directions. How? As initially these are randomly oriented, somewhere it was aligned in upward direction, dipole moments are not in, that means somewhere dipole moments are taken in this kind of direction, the random orientation, the net dipole moment can be 0. But when these molecules are placed, complete dielectric is placed in external field, so they will have their dipole moment along the direction of the field. So they are oriented in the direction of electric field. So this is a main concept. So hence polar and non-polar molecules develop a net dipole moment in presence of some external electric field. So this is basically called polarization of dielectric. So now this polarization we represent it by P. This is defined as dipole moment. This polarization is defined as dipole moment per unit volume, and its magnitude is also taken as polarization density. This will be, as a concept, will be used in the next case we will discuss. So polarization P, which we are defining, is dipole moment per unit volume, and another term which we take for it, that is polarization density. So basically here what we have to study polarization of dielectric, especially we will discuss here for non-polar dielectric. Then here we will study polarization of dielectric. Polarization of dielectric. So here this is the external field which we are maintaining by certain source, let it be E0, producing electric field. When a non-polar dielectric is placed in between, so as due to the presence of the field, its dipoles are arranged in such a way that negative charge is pulled opposite to direction of field and positive charge is pulled in the direction of field. Here as we have taken, I'm just drawing it again because it is not giving you broader view, it may confuse, it may leading to any confusion. Like this is the main concept. Now you will get clarity. Here when the external field is applied, so this is plus, this is minus, this is external field. So what will happen? As the non-polar molecule get aligned such that negative charge on one side, positive charge on another side, with the presence of external field, negative and positive charge get separated. Let me take few more molecules. Here it is clear that the separation of charges, few more molecules we are taking. Now what is the basic reason of drawing such kind of thing? As we are taking that the center of positive and negative charges are separated and polarization of this dielectric takes place. So what will happen due to this? As due to this positive charge, negative charge will be induced on this side. It means all the negative charge will be induced on this side and positive charge on this side. Now what will happen in between? This is positive, this is negative, and this is the central one. We have taken 3 molecules in each row, but exactly there can be any number of molecules within a dielectric, we cannot judge it. So here what we are getting, that correspondingly from this we are getting that there will be some induced electric field, and this induced electric field that is developed on it, being positive charge on this side, negative charge on this side. So this induced field, this will be given by EI. You can represent it by EI or EP. Again, I am taking this point. Since positive charge is induced on this side of the dielectric which is placed, and negative charge is induced on this side when a dielectric is placed in between some external field, then due to this electric field which is developed within the dielectric, that is opposite to direction of external field, and we will take it as induced electric field, EI, induced. EP also polarized electric field or induced electric field. So now, as per this diagram, this is E0 in this direction, EI, induced field in opposite direction. So the resultant electric field will be E0 minus EI. Net field will be this one. So in this way, this polarization of dielectric takes place. So now, here, as we have already discussed the concept of dielectric constant or relative permittivity, as here we are familiar that the dielectric constant is defined as the ratio of electric field and any original electric field to the reduced value of the field. Reduced value is E. So this is taken as the dielectric constant. So now this will be E0 upon E0 minus EI. This is dielectric constant which can be explained on the basis of, you can say, this electric field and reduced field. Now, another term which we are taking, actually here we have introduced the concept of polarization of dielectric by inducing opposite charges on the opposite sides of dielectric, and hence the electric field within it gets reduced. Now we are doing another term, this we have already introduced, that is polarization density. We have taken it by polarization or polarization density. As we have initially defined it as, it is induced dipole moment. Dipole moment per unit volume when a dielectric is placed in an external field, and this is taken as the polarization density. So as we are recalling the concept we have discussed now, here you can say that when a dielectric slab of area A and thickness D, area A, thickness E, is induced between external field. So now here it is here certain charge is induced, so you can say that when placing in between external field, this dielectric slab acquires surface density plus sigma I or minus sigma I. That is, this will having minus sigma I and this is having plus sigma I. So sigma I or sigma P, any symbol you can use, this is equal to Q, polarized charge, divided by area, charge per unit area. Now what will be the dipole moment on the slab? This will be equal to QP into separation distance that we have taken, D. So now as per polarization density, it is dipole moment, that is QPD upon volume of dielectric, and volume of dielectric is A into D. So now what you are getting, QP upon A. You can see here this polarization, it is equal to surface charge density. So therefore this polarization density is also defined as charge induced per unit surface area, or it is taken as surface charge density. This is basically a mathematical result that will be used further. See, just I am recalling it again, I am revising it as polarization density. By the definition, this is dipole moment per unit volume. So when a dielectric is placed in between external field, then induced field will be developed on it, and hence the charges present on this this dielectric, that will be whatever be the charges. So corresponding, let the charge induced is QP or QI, whatever symbol you can use for it. This is minus QP, this will be plus QP. So correspondingly, charge density will be charge per unit area. So correspondingly, as the charges are separated, there exists some dipole moment, because negative charge on this side, positive charge on this side. So dipole moment will be charge multiplied by distance. Now as per the definition of polarization density, substituting dipole moment and volume, you will get this is equal to surface charge density. So now here, what is the SI unit of polarization density? Yes, as it is charge per unit area, so it can be coulomb per meter square. Now, next is electrical susceptibility. Basically, this concept which we are using, as we know that polarization, what will be the polarization of the specimen, that is dielectric we are taking, it is directly proportional to resultant field existing within the dielectric. So this polarization is proportional to the reduced electric field. Now when we are removing this proportionality sign, we are getting a constant that is taken as epsilon naught into chi. This chi symbol, this is basically a proportionality constant, which this chi symbol is called electrical susceptibility. How easily the dielectric can be polarized. Basically, such kind of behavior can be judged by it. Now here, why this epsilon naught factor has been used here? Basically, multiplication factor epsilon naught is used to keep this electrical susceptibility dimension less. So this is only for the value that we have taken this polarization P equal to epsilon naught xi into E. Although this is taken to be a constant, this product is making so that this chi should be dimensionless. Now here electrical susceptibility, from that result it will come out to be this polarization divided by epsilon naught electric field. So the ratio of polarization P to epsilon naught times electric field, this is called electrical susceptibility of dielectric. So now we have to just learn this particular definition, the concept, the formula of electrical susceptibility. Now on the basis of the concept of this electrical susceptibility, we will establish the relationship between dielectric constant capital K and electrical susceptibility. Now, so here we are studying relation between dielectric constant and electrical susceptibility. As we know that the reduced electric field is given by E naught minus reduced field, which can be EI or EP, anything we can use. Now, as we have taken that electric field, this we know between the plates of capacitor or between these two plates, that will come out to be sigma by epsilon naught. So it will be sigma P. And in the previous derivation, we have already explained it that this P polarization will be equal to surface charge density. So you will replace it by P. Further, here by using the concept of electrical susceptibility, we have taken this P is equal to epsilon naught chi into E. So here EP can be taken as epsilon naught chi into E by epsilon naught. So it will be chi into E. Now put this value of EP in equation 1, first equation. So reduced field, we are taking only the values. So here it is E naught minus EP, EP is chi E. Now this here in these two, E is common, so we are taking it on the left side. E plus chi E, this is equal to E naught. So here when we take E as common, 1 plus chi, this is equal to E naught. So now 1 plus susceptibility factor, it is E naught upon E. Now what we have to derive here? Here we are finding relation between dielectric constant and electrical susceptibility. So E naught, electric field in between, or you can say when the air or vacuum is there in external electric field to the reduced field. This ratio that we have already explained to you, this is dielectric constant. So this is the relation. The dielectric constant is equal to 1 plus electrical susceptibility. See, many a times it can be said that this relation is not in the syllabus, but I will always cover it Reason being because the concept is introduced. So the electric constant we are familiar. We cannot leave this particular derivation because it is only on the formula substitution based concept. So this is the relation. Now next is dielectric strength. What is dielectric strength? Strength, maximum value. So basically dielectric strength, actually you can say use dielectric को when we are placing in between the electric field, then how it is handled in between. That means what it is handling. So the maximum value of electric field, that a dielectric can handle, withstand without breaking its insulating properties. See, we have already explained that dielectric is insulating material. So when a dielectric is placed in between external electric field, so this is the strength, this is a tendency of dielectric that can judge that the maximum value of electric field which it can bear, it can withstand without affecting the insulating property of this dielectric. So this is basically the concept of dielectric strength. This is the definition part. This can be asked, define dielectric strength. Now what will be its unit? Yes, because we are taking it is to be the maximum value of electric field. So its unit will be same as that of the field. So that electric field that you can take, that is, it can be volt per meter. As electric field is taken as potential gradient, so from here, from other way also you can define it. And more common practical unit of dielectric strength is kilovolt millimeter inverse. Now, when we are using this dielectric strength concept for safety purpose, the maximum electric field applied is only 10% of the dielectric strength. Meaning whatever be the maximum value that can be variable by a dielectric, but the maximum electric field that can be applied to that dielectric is only 10% of that maximum strength, because theoretical theoretical value and experimental value may vary. So that's why that means to withstand its insulating property, it is always required that whatever be the strength of maximum field a dielectric can hold, but when the field, within this field which we are in which we are placing it, the field applied will be only 10% of the maximum electric field which it can handle. This is one particular point, that is precautionary point. Now next we have to do derivation part. So capacitance of a parallel plate capacitor when dielectric slab is introduced in between the plates. So initially when no dielectric was introduced, in that particular case capacitance of the capacitor will be. See, each of the plate is having area A and these are separated by distance D. So when no medium was there, there is only air medium. So capacitance is epsilon naught A upon D, with plus Q charge and minus Q charge on the plates of capacitor. Now let me take a dielectric slab of thickness T such that T is less than D is introduced in between the plates of capacitor. So what will happen? The polarization will take place and it will acquire negative charge and it will acquire positive charge. So corresponding to it, here will be induced electric field or polarized electric field in a direction opposite to applied electric field. So it means now the electric field inside the dielectric will be some less than, by what amount? That it will be E naught minus EP. See how this is the external field, E naught acting here, but in between here EP, that is induced field, is acting in the opposite direction. So net field will be E naught minus EP. Now we know that K, dielectric constant, is E naught upon E. So this implies resultant reduced field will be E naught upon K. We will use this result. Now we have to find capacitance when a dielectric slab is introduced. So what concept should we use here further? As potential difference. We know the result that electric field is potential gradient. This concept we will use. Dropping the negative sign, we will use only mathematical magnitude only. So here you can see in between these two regions, total distance is d. Now up to t length, that is the thickness, here electric field is reduced. So what about in these two regions? This will have separation distance d minus t. So correspondingly, what will be the electric field present in between these gaps? So it will be E naught. The field applied, actual field applied in between the plates of capacitor generated by the charges, E naught into d minus t. Why d minus t? Because you can see in the figure, this is region and this region. This is forming d minus t. Whereas in between the thickness t, electric field is reduced. So reduced value magnitude is E and within the region t by using this result. This is the key point. Repeating that potential difference is electric field multiplied by the distance. So outside the, you can say, dielectric, between these gaps, the region d minus t, electric field is the E naught, whereas in between the dielectric, electric field is reduced, that is E. So now what you have to do here, put the value of electric field, reduced field from this result, E naught d minus t plus E naught by k into t. So now E naught we are taking common, d minus t plus t by k. Now electric field in between the plates, parallel plates, that comes out to be sigma upon epsilon naught. This we have done as an application of Gauss theorem, where we are finding electric field in between two sheets. Now here this is again d minus t plus t by k. Further converting this surface charge density into the charge. So it is q upon a, because charge on the capacitor is q. So here it is d minus t plus t by k. Now what we have to obtain? Capacitance. Capacitance is q upon v. So from here if you will calculate q upon v, it will come out to a epsilon naught upon d minus t plus t upon k. Further, here in the denominator, if we take d common, what we are getting? 1 minus t upon d plus t upon dk. Right? So here a epsilon naught d, this is capacitance. You can represent this, I have taken C, represented by C naught. This is capacitance of parallel plate capacitor when air or vacuum is in between. So you can replace this by C is equal to C naught upon 1 minus T upon D plus T upon dk. Further you can take T common. This will be T by D common. This will be 1 minus 1 by K. Right? So here C is greater than C naught. Now let me take one particular case. If T is equal to D, that means dielectric whose thickness is equal to separation between the plates. It will completely fill the gap. So in that particular case, see, as per this result, when T become equal to D, so what you will get? Here it is 1 minus 1 plus 1 by K. So it is K times C naught. Now it is clear how you are saying that C is greater than C naught. So when a dielectric has been introduced whose thickness is same as that of the separation between the plates, then the capacitance will increase. So this is an important topic. Result will be used many a times. Here you can see when you are finding capacitance of parallel plate capacitor with dielectric slab, electric field in between the dielectric will be reduced. And then what is the main point which you have to remember? That is the potential. This potential that is to be obtained in between the plates. As in between the dielectric there is the electric field is reduced, so it is E into T, whereas in between the gaps where the thickness is D minus T, here D minus T, this T minus T I can just mention it here that this plus this is d minus t. For this portion, electric field will remain to be the same, E naught. Now, substituting the values, rearranging the terms, you are getting the capacitance of parallel plate capacitor. Under one special case, we are concluding that capacitance is K times the initial capacitor. So this is the derivation part we have taken, few topics we have covered. Revise these topics because now within one lecture your all content will be complete and you have to do extra practice of conceptuals also. So keep revising the concepts and focus more on the written practice. Thank you. Have a nice day.